Oh shit, here we go again.
The beginnings of atomic theory are found around the 5th century BC. Leucippus is thought to be the earliest Greek to ever develop a theory of atomism, passing it down to his student Democritus. This early theory was utilized during centuries with various different philosophers and scientists, studying it as well as deciphering the structure of these so-called atoms. Some examples of these are seen through the medieval ages, but it wasn't until the atomic renaissance in the 17th century where scientists like Descartes, Gassendi, and Galileo brought a wider interest to these theories in the Western world. This atomic renaissance brought with it the theory of
corpuscularianism,
which was similar to the atomic theory established by the Greeks, but it said that atoms, which were called
corpuscles,
were not invisible. The theory was quite dominant over hundreds of years, thanks to Robert Boyd, who primarily developed this theory, and Isaac Newton, who was a strong believer of it. In the beginning of the 19th century, an English scientist named John Danton came to the conclusion that all matter was made of small balls, which were the fundamental particles of nature. This theory wasn't really unheard of, but Dalton had something new to bring to the table. He began differentiating elements by the relative mass of their atoms, stating that atoms of a given element are identical in size and mass. This means that Dalton thought that hydrogen atoms were all the same, and he was correct. Dalton also theorized that in chemical reactions, atoms were combined, separated, or rearranged. The sad thing is, most of his points in atomic theory were quite controversial at the time and were not widely accepted. Look at this ball. This is a hydrogen atom. No one believes you. Although his theory was very simple compared to the reality of atoms, Dalton had established something that no one could even begin to imagine. It wasn't until the end of the 19th century, with the discovery of the electron by J.J. Thomson, that scientists were able to create a more accurate description of atoms and finally establish the electron as a truly fundamental particle. In the 20th century is when things start getting wild. At this moment in time, scientists only knew two fundamental forces, gravitation and electromagnetism. So with this new discovery of a negatively charged particle like the electron, explaining how the structure of an atom worked was very challenging. The first thing that was hypothesized was that there had to be a positively charged particle somewhere so that the electron could be attracted into staying in the atom. In 1904, the Thomson model of the atom was established. This model looks very silly with what we know today, but it actually made sense back then. So, this is what an atom looks like, kinda like a soup, which is quite weird. That makes no sense, you old man. Who are you and how dare you oppose the great J.J. Thomson? Rutherford established his own atomic model in 1911. Thanks to the discovery of radioactivity by Marie and Pierre Curie, Rutherford was able to experiment with alpha particles with the gold foil experiment in 1909. These experiments explained how atoms were actually formed by a nucleus which was surrounded by electrons. Rutherford also theorized the existence of another particle which was later discovered in 1932 by James Chadwick. This particle is known as a neutron. 2 years later, in 1913, Niels Bohr, with the help of Rutherford, established a new model which to this date is the most used model. It's the 1960s and scientists are starting to believe that protons and neutrons are not fundamental particles, but instead they can be broken into new fundamental particles. One of the most known fundamental particles is the quark. The quark was first brought up in 1964 by Murray Gell-Mann and George Sway. Gell-Mann and Sway stated that the fundamental particles were the ones responsible for the creation of other particles that weren't understood yet, like the kaon and the pion, which had been discovered in 1947. Gell-Mann and Sway created a model of three quarks named the quark up, down, and straight, describing that the particles had properties like electric charge and spin. Later, in 1968, the quark was first detected in the SLAC. This discovery, along with the electroweak theory discovered by Sheldon Glashow, The comparison of Higgs mechanism by Mohammad Salam and Steve Weinberg and many other discoveries led to the introduction of this new model, which categorized the fundamental quantum particles, as well as 3 of the 4 fundamental forces. Now let's look at the standard model to understand it better. To make it quite simple, this model is separated into 4 categories, along with a hypothetical one. To begin with, we have the quarks, which are the fundamental particles which form other particles called hadrons. Protons and neutrons are both hadrons and are responsible for most of the mass of ordinary matter in the whole universe, like a car. Then we have the leptons. Here you can see our old friend the electron, with his friends the charged leptons and the neutron leptons, which are the 2 categories of the leptons. Charged leptons have the property of being charged. On the other hand, neutral leptons have no charge and are simply neutral. Charged leptons are mainly responsible for the creation of composite particles by combining with other particles. This is mostly observed with electrons being combined with protons and neutrons to create atoms. The next category we have are the Gauge bosons, which are very complex, so I'm gonna keep it real simple. To begin with, there are 4 fundamental forces in physics. These are the electromagnetic force, the gravitational force, the weak nuclear force, and the strong nuclear force. The Gauge bosons are able to explain all of these forces, except for gravity, which I will explain later. Gluons are the particles responsible for the strong interaction, which is the interaction between the strong nuclear force and particles like quarks, so that they are able to bind and create hadrons. Photons are the particles that are responsible for the electromagnetic interaction. This interaction is mainly responsible for the attraction and repulsion of charges. The Phi boson and the W boson are the particles responsible for the weak interaction, which is the interaction between particles that generate radioactive decay due to the weak nuclear force. The last category we have are the scalar bosons, which, as you may see, only has 1 particle in it. This particle is the Higgs boson. Now, this one is real complex, so I'm gonna do it the simplest I can, because even I can understand it. According to the standard model, all the Gauge bosons should be massless, but as you can see, the C and W boson both have a mass. This destroys the credibility of the standard model, as it couldn't explain how this happened. Scientist Peter Higgs later theorized that these particles were actually massless, but due to them interacting with an energy field we didn't know of yet, they gained mass. He called this field the Higgs field and stated that it exists all across our universe. Higgs theorized this in 1964, but this theory explained that this field was all over the place and it was very hard to detect. The main way scientists thought of detecting it was by exciting the field, therefore creating a particle, the Higgs boson. Due to our technology at the time, the Higgs boson was impossible to find. But with advancements in detectors and computers, in 2013, the Large Hadron Collider confirmed they had detected the Higgs boson. This made the standard theory gain its credibility back, thanks to Peter Higgs and all the scientists that worked on this theory, proving that the Higgs boson existed. Now, you may be wondering what I meant when I said there was a hypothetical category. As I said before, the Gauge bosons were able to explain 3 out of the 4 fundamental forces of matter. Well, the thing is, there is no particle that explains gravity. At least, we haven't found it yet. It's only theoretical, but it's called the graviton, and it hasn't been detected yet. Due to Einstein's theory of relativity, our perception of gravity has changed, and explaining the graviton has become complex due to the fact that mathematically it has some discrepancies with general relativity. Many scientists consider that gravity is not part of the standard model and that the graviton doesn't exist, as gravity is explained through general relativity. Other scientists consider that the graviton would complete the standard model and is an important part in explaining how our universe works.